In this video, we're going to talk about something called the Arrhenius equation. The goal of this is to look at the impact that temperature has on our kinetic rate constant. So for a reaction, sorry, something disappeared on my screen. There we go. So for a reaction, sorry, I was trying to draw something I did. Okay, so for a reaction, what we'll do is we'll have something that looks like this, where the y-axis is going to represent energy. The x-axis is going to represent something called our reaction coordinate. Now, in a lot of textbooks, and I know the one I'm currently using does this, they actually just don't mark the x-axis at all. They just kind of go, don't worry about it. So what we're going to use the x-axis to represent is where we are in a reaction. So are we at the reactant side or the product side? It means you go across the x-axis, you're going towards that. Now, you can define this some other ways. Usually it's about like how far all the atoms are moving compared to each other, because in the process of getting to reactants to products, the atoms have to move around some. So it's usually related to that, but we're just going to worry about the start and the end, and then about the energy part that happens in between. So reactions will many times look something like this. So the top will be the reactants, or the start, not the top. The start will be the reactants, the end will be the products. And this barrier in the middle helps explain why you don't just always just have products. Because things should naturally go to their lower energy configuration. So if you didn't have activation barriers, it would be strange to see things in the reactant state like here, ever. Because you'd just be like, well, why doesn't it just go to the lower energy? So our system needs some energy to overcome this barrier. Now the idea of the barrier is when you have two molecules, like let's say you're combining hydrogen and oxygen. So let's say we have H2 plus O2, and we want to use them to make water. Well, you can't just take the hydrogen and oxygen and like rip an oxygen off and put it on. So the atoms have to collide in some way, and when they do that collision, they're going to temporarily form some new bonds before they form water. Temporarily, it's going to be in a much more unstable state, and it depends on the exact chemical reaction, exactly what that configuration looks like. But that's going to occur at the top of our peak here. We call that a transition state. So it's going to be something temporary. We're usually not going to see it. There's some neat spectroscopy tricks we can do to try to capture things in transition states. But if you were to just take some hydrogen and oxygen and you were doing a reaction to turn it into water, and you were to stop the reaction somehow, you wouldn't find things in the transition state. You would find things as either the gases or as water, not in between. So this isn't something that is stable that you're going to see in your products ever. You're not going to look out and go, oh yeah, I have this, 1% of all my reactants by things aren't reactants or products. They're actually transition state materials. You won't see that. It's very, very short-lived. But the idea behind it is you can't just go from hydrogen, oxygen to water. You need enough energy in your system to be able to overcome this barrier. And the reason we're worried about that is we can actually figure out how much energy is needed for that barrier using the Arrhenius equation. Now, you can also have reactions that look like this, where you go here, and you end up over here, where you actually do end up at a higher energy. That can happen as well. And we will talk about that later in the semester, sort of why, when we get to more thermodynamics, why in the world you might see reactions where the products actually have higher energy. That feels weird, but we'll talk about it when we go to the difference between kinetics versus thermodynamically favored reactions. So we will be doing some more looking at that towards the end of the semester. But just note, you can have either one of these, and this has to do with whether it's an endothermic or exothermic reaction. Determines which one of these it is. Is it having to absorb energy, or is it releasing energy if we compare the reactants and products? We also looked at that some in 1211. Remember, some reactions absorbed energy, some released energy, and we used figures like this to represent them. So now, we want to know how much energy is there in this difference thing here. So this difference is called EA. It is the activation barrier to our reaction. So we actually have an equation for this. So the Arrhenius equation is that the natural log of the rate constant is equal to the negative EA, which represents our activation barrier, divided by R. That's our gas constant, which in this case we'll use 8.314 joules per mole Kelvin, because it works with the units we're working with. And then you have 1 over T plus the natural log of A. A being this thing called a, oh gosh, I suddenly forgot the name. the orientation factor. Yeah, there we go. So we have that. This equation, you may notice, looks a lot like the Clausius-Clapeyron because it is also taking an exponential equation and turning it into a linear equation. So this matches up with the idea of y equals mx plus b. I highlight this because that'll help out when you look at graphs of this or do this in lab. X is 1 over t, y is natural log of k, and then the m is there, and the b is the natural log of the orientation factor. Is orientation factor? No. Okay. So we have that. This version works really well when you graph it. And if you've got a lot of data points, you can put them in Excel and create a graph, and it works pretty well. However, in some instances, what we want to do... Okay, I want to pull something up real quick. Not that. That is not it. Okay, I have something on my screen I want to check real quick. Yeah. Sorry, it is called the frequency factor. I used the wrong word. It is the frequency factor is what A is called. That has to do with how many times the molecules collide. And there is another form. We also sometimes write the equation like this, that K is equal to A times E to the negative activation energy over RT. So all that stuff is in the exponent, the EA, the R, and the T. So note both of those are okay. They are both usable, and we'll use them in different forms. Now, both of these are good for things like graphing. I also want to highlight that it shows that K, once we start changing temperature, K changes. So in a lot of problems, we dealt where temperature didn't change, so we said, oh, K is a constant, which was true there. We don't change something about how the reaction's functioning. We just change the concentrations. K doesn't change. It's not dependent on the concentration. But once we start changing T, we can't use the same K. We have to recalculate K. So in a lot of instances, we might want something that looks a lot like the Clausius-Clapeyron two-point equation we looked at. So we can also take this equation and turn it into something that looks like that. So we have the natural log of K2 over K1 equals our activation barrier divided by R times 1 over T1 minus 1 over T2. So this is the two-point form. It works really well when you have two rate constants and two temperatures and you want to find the activation barrier, or you already know the activation barrier and you know a rate constant and you want to find a second one. So then you look at a different temperature. Or in theory, if you really wanted to find a specific time where the temperature, where the reaction rate constant was something, you could have the temperature being the unknown. That's less likely just to come up practically speaking, but you could do that. You could calculate that. So this is our other form we can work with. And this is the one you're most likely to use when you solve problems. They tend, if they're not graphically based, or it's not something like you made a measurement in lab, because it is easy to work with. It only takes 2 points and you don't have to use a piece of graphing software. But the graphing version is very helpful in terms of that's something we will very commonly do practically speaking. We will make a bunch of measurements, then try to figure this thing out. So let's take a look at how do I use this equation and what can we do with it. So we have this problem here. We have a reaction that has a rate constant of that number at 25 degrees Celsius and another number at 55 degrees Celsius. And we want to determine the activation barrier for this reaction. So a good way to know that we probably want to use the Arrhenius equation is the fact that we have anything to do with the activation barrier. There's a good chance it's going to come up. Once you have two temperatures, you're very likely to have to deal with this because anything related to the rate constant, if we've got multiple temperatures, this is the best way to deal with that. So these are good hints of, oh, I've got two temperatures, or I'm worried about a temperature somewhere. That's a good chance it's going to be what works here. So I'm going to go back and I'm going to set up my equation. So to figure out the top question, we have the natural log of K2 over K1 equals our activation barrier divided by R times 1 over T1 minus 1 over T2. I also want to comment, if you watch other people's videos or look at other people's resources, there's a chance their Arrhenius two-point equation looks a tiny bit different. That's because they can use our rules of logs and negative signs to move some of these things around. Like maybe they have a negative in front of something, but then they flip the order of the T1 and the T2. Well, I could do that. Or they'll flip K2 over K1. You'll sometimes see it as K1 over K2. But then they'll also go over to the temperature part, and they'll flip those as well. So you may see this in slightly different forms. Just make sure you're using a single form. Because the problem comes up if you like try to remember it from your head and then you mix two of them up and you don't flip everything right, then you end up messing up with the negatives. So if you're unsure, just use this form, or one that's in your own textbook. Use that one consistently, and that'll be good patterns and make sure you're doing okay. But do know it's not that the other person has it wrong or that mine is wrong. It's that you can do multiple forms of this by moving the negatives around, and then you flip things inside of your logarithms, or you move things around in your parentheses when you distribute your negative. So that was a bunch of stuff to say. This may look a little different in some places. Let's look at our problem now. So I'm going to make this number K1. You just have to be consistent. So that means this is going to be T1. And specifically, I'm going to convert it to Kelvin. So it'll be 298.15 Kelvin. This will be K2. And that means my T2 is going to be by 55, which is going to be, I lost my pen again. There we are. So my T2 is going to be 328.15 Kelvin. Make sure you don't forget that part. So now, at this point, you can either plug all the numbers in, or you can rearrange the equation first. In this instance, I'm going to rearrange it first, but if you like plugging numbers in first, that works okay here. So I'm going to start. I need to do two things. I need to multiply both sides by r, and I'm going to divide by the whole thing 1 over T1 minus 1 over T2. I'm doing that to get EA by itself so I can solve the activation barrier. So when I do both of those things, I will get r times the natural log of K2 over K1 divided by 1 over T1 minus 1 over T2 is equal to our activation barrier. Now I'm going to plug some numbers in, and my camera's going to go away so I don't accidentally block the numbers. So when I plug things in, R is going to be 8.314 joules per mole Kelvin. We're going to multiply that by the natural log, there we go, of, let's see, our K2 was 4.76 times 10 to the negative 1, S negative 1, and then our K1 was 1.85 times 10 to the negative 4th. Note, make sure you're paying attention to which goes on top and bottom. It's very easy from other patterns to accidentally put K1 on top here if you meant to put K2. So just don't let that happen to you. And then I have 1 over 298.15 Kelvin minus 1 over 328.15 Kelvin. And all of that is going to be equal to our EA value. So this is just where we've got to put a lot of things into our calculator. So the main thing here is to be careful and make sure that we're putting everything in correctly. And without looking at your work, I can't tell what it is. But if you got to this step, you've done the most important part in my view. But if you end up having trouble getting the right answer, it could be that you just need to look at how you're plugging things in, that something's going wrong there. So I'm going to do it in two steps. So I got my numerator was 65.2883. I'm purposely keeping extra digits because it's very easy with logarithms and exponentials to accidentally round too much and you end up getting a value that's pretty far off. So I like to keep a couple extra digits at the beginning, and then I'll round at the end of the problem. Ideally, just keep it all in your calculator if you can. And the denominator is going to be 3.0663 times 10 to the negative 4th. And this is in Kelvin, and this is in joules per mole Kelvin. And sorry, this is in inverse, Kelvin negative 1. So those kelvins end up canceling, and so we'll be left with joules per mole at the end. So we have 65.2883 divided by that number at the bottom. And so for this, I got, let's see, it looks like I'm going to have about 3 significant figures. I'm going to have 213,000 joules per mole, or 213 kilojoules per mole. So I write that to make sure you know that you'll many times see these things when you look at the numbers in kilojoules per mole. So the really big answer can feel off, but it's not. It's just that it was in joules, and that's you have a lot more of those to make up a kilojoule. So I'm going to write that up here, that we have 213. Actually, I'm just going to erase everything on the slide real quick. And 213 kilojoules per mole is what we're working with. So let's clear that out. Because now we need to work at the second part of the problem. So we have 213,000 joules per mole. And I'm going to leave it like that so it'll work for the unit. So part 2 is to find the rate constant at 15 degrees. So to do that, you use the same equation. So I do have to rewrite it. We have the natural log of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2. But now what we're doing is we're going to make this T2. So that's 288.15 Kelvin. And so we're looking for K2. That's what we don't know. Now you can choose either of the top numbers to be K1 and T1. It doesn't matter. So I'm going to make this K1, and I'm going to make this T1, which was 298.15 Kelvin. You could have made it the other number. Just be consistent. So now we need to solve for the K2 in here. So for this one, I'm going to start by undoing my natural log. So I raise e to this power, and I do this on both sides. And that's going to make this cancel. So I will have K2 over K1 equals e to a giant power with a whole bunch of stuff in it, right? EA over R times 1 over T1 minus 1 over T2. And I know it looks a little funny for you possibly if you're not used to working with expressions with that much of an exponent, but those are all just numbers you're going to plug in. And so finally, I want K2 by itself, so I multiply both sides by K1. So if I multiply by K1, that'll make those cancel, and that'll put a K1 in front. So now let's plug in a bunch of stuff. So K2 equals E to the, so EA is 213,000, and I'm going to use all the numbers from my calculator actually, so to make sure I don't have a rounding error. So this is 212,922. You could use 213,000, you should get pretty close, but I'm going to use this just to make sure. And then it's divided by 8.314 joules per mole Kelvin, and that's in joules per mole, times 1 over 298.15 Kelvin minus 1 over 288.15 Kelvin. So in terms of units, when we subtract these, we're going to get k to the negative 1, and that will end up canceling with the Kelvin down below here with our R, and then the joules per mole will cancel. And it'll be unitless when we take e to a unitless number, which will work out fine because it's an exponential. So that will work out for this part, and we are going to get that K2. And, oh, right, I forgot the K1 in front. So we have, sorry about that, we have 1.85 times 10 to the negative 4th inverse seconds. I'm just trying to give you the real in-class experience, because as a professor, I definitely have times where I forget some number there. So I was just doing that, keeping you on your toes, right? It's not that I made a mistake, which I clearly just did. But we caught it before the end, which is the important part, right? When you're solving these problems, you catch it in the middle because you've done a lot of practice, and then you'll fix it. Otherwise, you'll just work real fast, you won't notice, and then you'll miss the problem. Now I got a lot of stuff to put in. So so first I'm going to do this the temperatures. So I'll put all those in. These take a while. Okay. So for this little section here, I got negative 1.16398 times 10 to the negative 4th. Now we got to multiply it and divide it by the other two numbers. So dividing it by 8.314 and multiplying it by 212,922. And when I do all of that, so this whole thing, let's circle the whole thing. This whole thing here, I get is equal to negative 2.9810. That'll work well enough. So I'm doing e to that power. E. And that gave me 0.05074, and I'm multiplying that by my 1.85 times 10 to the negative 4th. And what I got is that K2 is 9.39 times 10 to the negative 6, because now I'm rounding to my 3 significant figures that my other K values have. So this is at 15 degrees Celsius. Okay, and that went the direction I expected. So the rate constant's going down. It's getting smaller. Remember, it's got a more negative exponent, so this is a smaller value than the value at 25, which is the direction I would expect. As when it gets hotter, the value goes up, like it did at 55 degrees. It got to negative 1, that power. So this checks out with what I would expect. Now, I have one other thing I want to show you with these. We're not going to work this problem here, but I want to show you another way they can be worded. So a reaction doubles its rate constant when the temperature changes from 12.5 to 24. What is the activation period for this reaction? So I want to point out that you can think of this equation in different ways. So we're not going to solve the whole thing, but I want to show you the trick that makes this work. And it's not really a trick, but it's the math logic, how to think through it. So we write out our equation. And initially, this looks like it wouldn't be doable because they've told us T1 and T2, but we don't know we've got both K2 and K1 being issues. How would I work with those? Well, what they've told you is a reaction doubles its rate constant when the temperature changes from 12.5 to 24. That means that we can relate K1 and K2 to each other. Specifically, when you go from 12.5 to 24, you double its value. So, when we're doubling the value, that means that K1 is going to be twice as large, or K2 is going to be twice as large as K1. So I would need to double K1 to get the value from K2. The reason this matters is you can then plug it into your equation, and what you can do is you can replace K2 with 2K1, and then the K1s cancel, and you're left with natural log 2. So remember, you can use algebraic manipulations. And so it's not because I think you're necessarily going to have a problem that is exactly the reaction rate doubles. Oh, that means 2K1 equals K2. It's because I want you to see that depending on the wording, you need to think through how could you do an algebraic insertion to help to deal with the information they gave you. That it might not just be, oh, K is this and K is this. So you could have tripled it, then it'd be 3K1 equals K2, but it could also be some other type of relationship. So this is an example of how else that can come up. Now, to finish up this section, I have a tiny bit I want to talk about. There aren't more problems. But I want to mention how it is we think about how kinetics works and what's causing reactions to happen. So we have something we call collision theory. So the idea behind collision theory is that molecules need to have to run into each other to be able to have reactions happen, and they need two things. One, orientation. So they have to be in the right direction. So for example, let's take a reaction where you have 3 atoms connected to each other, and one of them is really big and 2 of them are small. And let's say the products we want to get are that the 2 big atoms come together. Well, if they're supposed to come together in the end, they need to point at each other when they hit each other. So if these 2 molecules collide with each other, that can work because the big molecules are hitting each other, they can stick. But let's say we had our 2 small molecules, or big atoms in our big atom, and then it ran into the molecule this way. And they hit each other, that can't happen. Well, I mean, they can hit each other, but they can't react correctly because the big atoms aren't touching each other, so they won't form a new molecule. So the first thing that helps determine how likely our reaction is to happen is how difficult is it to get it in the right directions so that they fit together and they make the new molecule. How restrictive is it? So some setups are going to be much less restrictive. It could be that they can orient in a lot of different factors, and others will be really, really specific. The second factor we have to worry about is, do we have enough energy? So if our reaction, when they run into each other, there's not enough energy to break the bonds and make the new ones to overcome that activation barrier, you're not going to have a reaction. So for the second one, we heat up our reaction, we provide more energy to the area, it's more likely to have enough energy to be able to overcome that barrier. So these are the 2 types of things that impact. So this is how to think of conceptually how we think about why do reactions happen versus why do they not. They need to have enough energy and they need to be the right orientation. If both of those things happen, it is an effective collision, and then then a reaction can occur. So it's important to realize that at room temperature, molecules in the air, for example, hit each other a lot, like hundreds of thousands of times a second. So from that perspective, you can have a whole lot of these that are ineffective and still get a meaningful amount of product. So a lot of times the reactants may hit each other and not react, but that doesn't mean you don't end up having a product. There are also things we can do to affect this reaction to improve how likely these are to work. In terms of substances, we use things called catalysts in many cases. And I'll explain why I say many cases. So a catalyst can work in 2 ways. The most common is something called a positive catalyst. It helps a reaction happen. So imagine, from the last slide, we need the 2 big atoms to hit each other. So imagine you had a catalyst that was on let's say it was a surface, for example. And it had something that could grab on. So it had some arm, not literal arms, right? It's like a molecule of some type. My arm, this is represented, that holds on to this atom here. And then we have other things on the surface that holds onto this atom here. And let's say these are just the right distance apart to help them collide into each other. So we got our little atoms and our little atoms. And let's say they're oriented to try, and the two attachments somehow are oriented to try to keep these things close to each other. Whatever it might be. So obviously most catalysts, it's a little more complicated than that, but this is the basic idea. They can try to orient everything in the right place. Also, when you do this, it can help with the molecules finding each other. Because maybe this arm holds on to it, and maybe there's not a lot of reactants in our system, but it's going to hold on to it till another atom comes, another molecule comes, and they combine. So even at really low concentrations, this can help the molecules find each other. Because at low concentrations, they're not as likely to collide. So you can also think of this, for example, with enzymes that happen in your body. So you may have molecules that aren't incredibly common that have trouble finding each other, but the enzyme can bring them together. Or maybe you're working with things like proteins that are incredibly complicated orientations. They have lots and lots of atoms, and so trying to get an effective collision is really, really hard. But you have an enzyme that brings the two molecules together and gets them to collide into each other in exactly the right orientation and hold them there at the right spot so they're able to react. And the enzyme is probably designed them, once they've reacted, they're no longer attracted to the enzyme and they'll pop out of the enzyme. So that's how that works. Now that's a positive catalyst. You can also use a negative catalyst that makes it harder for this reaction to occur, which you don't see as much, or at least we don't talk about them as much. They don't. But you can also do that. You can make it so that something interferes with the reaction. And what's important about both of these is you'll notice the catalyst is not a reactant or a product. That means it doesn't get used up. It doesn't show up in the balanced chemical equation on the left or right side, but it's still key and it affects the rate constant. So if you have a catalyst present, K is not going to be the same. It's going to change the value for K. In the case of a positive catalyst, it's going to speed it up a whole lot. A negative catalyst would slow it down. So this ends what I'm worried about in terms of discussing topics for the area of kinetics. And so those of you following along with my series, we'll be going towards equilibrium next, which is a fairly large topic that we will spend multiple chapters on in a number of videos. So I hope this went well, and I will talk to you soon.